Larry, please feel free to start.
Thank you. I want to thank you for inviting us to give this talk. Herbert and I have worked together on this problem for quite a long time, and we were, these are real world problems that need a solution, and we've heard some cases today where people needed solutions for this. So let me see, I don't see how to change the cursor. Mine's big enough anyway. There we go. So the problem is, there's lots of lattices. This is a nice two-dimensional lattice. But how do you compare this to a tiled floor? And it gets much harder when you get into 3 dimensions. And in higher dimensions yet, it's an even more difficult problem. We'll talk about that briefly. So in a lattice, there's lots of possible unit cells. We've actually seen this in Graham's talk, where he had 2 triclitic cells that were very different. So how are you going to compare them? Reduced cells are one of the ways, and this has been a standard way for a long time. There are 4 different kinds of reduced cells. The Dirichlet cell, the Minkowski cell, so these go back to 1850 and 1891. Niggli, which has become kind of the standard in crystallography, and Delaunay, both around 1930. Minkowski reduced cell in an n-dimensional space is the n shortest basis vectors. The interesting thing is that this is actually the basis for a lot of cryptography in the modern world, because in order to do the factoring, they are actually finding the base vectors in a high dimensional space, and it's an NP complete problem, and it's difficult. The Niggli reduced cell is the Minkowski reduced cell, specialized for 3 dimensions, with the 3 cell lengths sorted. It has the shortest A, B, and C of any lattice triple in this lattice, and the alpha, beta, and gamma, the angle between the axes, are changed to be either all obtuse or all acute. It's also described as the most acute, the most orthogonal unit cell. The Delaunay reduced cell is a little different. It starts by defining a vector D for diagonal that is the negative of the sum of all 3 of the basis vectors. And the cell is based on the 6 dot products of A, B, C, and D. One of the consequences is of the reduction process is that A, B, and C will all be obtuse. This was actually discovered by Brevet in 1850. Selling, then it uses what is called Selling reduction based on Selling's 1874 paper, specialized for 3 dimensions. And it basically takes the metric tensor for those 4 vectors, A, B, C, and D, and minimizes the sum of the off-diagonal elements. The Dirichlet cell chooses a lattice point, and it's all the points closer to that than to any other lattice point. Delaunay showed that there are only 5 different shapes, things like cube, truncated octahedron, things like that. And this cell has other names. It's also called the Voronoi cell, the Wigner-Zeitz cell by material scientists oftentimes, and it's the Brillouin zone in reciprocal space. So the story of unit cells goes back a long way. Probably the beginning of this is Kepler in 1611 writing his paper about snowflakes, and then Steno writing about crystals in the 17th century. In 1800, we have Aui, who made a catalog of a cabinet of crystals. And then through the 1800s, there were databases of the interfacial angles of crystals being assembled. And then starting after the discovery of X-rays, people started making catalogs of the unit cells. We have Niggli and Delaunay coming along about the same time, and they figured out how to convert the information about the reduced cells that we talked about earlier to identification of the Brevet lattice types. And then in the late 1870s, the Chemical Information System, a database that was being put online by the National, the NIH, National Institutes of Health, and the EPA, Environmental Protection Agency here in the US, was being put online. And they asked us to create a database of the known unit cells at that time. Why do we want to compare lattices? One is the Brevet lattice determination. This is really one of the first stages that happens in crystal structure determination. There are databases of unit cells and you want to look them up. And I have a story to tell there. When I was writing that database for the Chemical Information System, I had the first copy of it running, and a friend who was also a postdoc with me at the time was a wine lover and found that the wine that he loved had crystals in it, big crystals sometimes. And he wondered what they were, and we had no way to figure it out. So I said, get me the unit cell parameters and we'll see if it's in the database. And sure enough, it was calcium hydrogen tartrate. It's right there in the database. In those days, we only had a few tens of thousands. Now, look at CSD, there's over 1 million, and there's a huge number in the protein data bank too. Also used for studies of twinning, and it has suddenly become important in serial crystallography, first at the X-ray free electron lasers, and then at the synchrotrons, where there are hundreds, thousands, and sometimes hundreds of thousands of images taken. And they have to be grouped together because there are polymorphs of proteins and there are things that aren't even crystals. And they make dendrograms to work out which ones should be grouped together. So in 1978, there wasn't any algorithm for comparing lattices. The only thing that was being done basically was compare the 3 axial lengths. And if the angles matched, that was nice. And if they didn't match, you didn't know if it was the same thing or not. So we created a vector that took the 3 shortest lengths, the reciprocals of the reciprocal lattice vectors, and we would reduce the reciprocal cell and took the cube root of the unit cell, which gave 7 parameters that were in the units of angstroms. The interesting thing is these are stable to distortions of the unit cell. So you change the unit cell a little bit, you're going to change this vector only a small amount. And the volume is an invariant of the unit cell. All primitive cells in a lattice, doesn't matter where you choose it, have all the same volume. And in 1978, we put the Chemical Information System online. The advantages, it was stable, it's simple to compute, just 2 Niggli reductions and a volume calculation. The database building is rapid, the retrievals were rapid. But it had problems, and we only became aware of this later. At 90 degrees, the sensitivity goes to 0. The sensitivity to angle change. Unfortunately, there's a lot of 90 degrees in crystallography. The correlation between the real and the reciprocal lattice parameters is often large, and it can approach 100%, especially in the 90-degree range. So how do we calculate the distance between 2 points? Let's look at a lattice first. So we look at the unit cell, and there's some distance between atoms A and B. That's got to be a good first guess, but there might be a B atom in the lattice closer. Oh my, I have a font problem here. So we have to look at all the distances from A to B and find the shortest one. And then the next thing we can do is we can go through here and cut out these segments and move them back into the unit cell. And then we can do an embedding. We can wrap this up into a torus, and people are usually pretty familiar with this. We go out here on this boundary, come in on this boundary, go out on that boundary, come in here. And of course, you can wrap that up into a torus. So that's one of the ways of getting the shortest path. Now, an embedding like that has problems still. There's lots of geodesics. All the different ways that you could go from an A to a B atom in that lattice are still there on the torus. You still have to figure out how to find it. And the next thing we're going to talk about is the spaces G6 and S6 that we wrote to handle how to find unit cells. And they're not lattices. The boundary transforms on some of them may not be unitary. And the other problem is we don't know how many boundaries we're going to have to examine. Excuse me. So we started working on what we call G6. We created this space in 1988. It's based on the Niggli reduced cell. So we have the minimum lengths, and we have some guess at angles. And we made a vector composed of the elements of the metric tensor, a squared, b squared, c squared. And because there's 2 entries for b dot c in the metric tensor, we multiply by 2, and same for this. The problem is that some of the boundary transforms in this space are not unitary. The Niggli cone is not convex. I said earlier, in the Niggli cell, we make all of the angles either acute or all of them convex, obtuse. And the connection between those doesn't always contact. There are 15 different boundaries. There are several types. And some of the boundaries have portions that are topologically open, and some of them are closed. We published this with full description of all of the boundaries in 2014. So then we started to think about Delaunay's reduction. And we based a space S6 on Delaunay's reduction. And the parameters, the scalar parameters in this space are going to be b dot c, a dot c, and a dot b. Notice for mnemonics, this involves alpha, beta, and gamma. And then we include the 3 dot products of A, B, and C with D. So we get the dot products with A dot D, B dot D, and C dot D. Has some advantages. The space is homogeneous. There are 6 dot products that are all very similar to one another. The fundamental unit in this space is the all negative orthant. It's convex. Doesn't have the problems of the Niggli reduced cell. And there's only 6 boundaries where each of these 6 can be 0, and there's only a single type. They all have the same kind of properties. It also turns out that it's much faster to calculate the Delaunay reduction than the Niggli reduction. One of the problems in this, there's 24 reduced copies. If we go back to here, these can be, the scalars can be interchanged in certain ways, 24 different ways, and they're all reduced. And each boundary has 4 different transformations that could be applied when they're crossed. So how do we calculate distance? The first thing is just measure it in the fundamental unit, and that is an upper bound on the distance between the cells. You have to check that the reflections, the 24 reflections, one of them could be better than another. Now, it's not always 24. Sometimes it's less, especially if there's 90-degree angles. And then you have to start the process of looking outside. Back in that lattice, A dot B, we had to look for all the B's. Here we have to look for other unit cells. So we've now come up with software. It's a feasible matrix. It's fairly fast to calculate. But we're getting more and more CPU speed, and core counts help. We also have a database online called SAUCE that was also in 2016 that uses this, among other metrics, to look at a database that is all of the COD database of unit cells and the protein data bank. And it's being used in some research for at synchrotrons to get starting points for structure determination. Now, if we think about how to do an embedding in this rather high space, we know from Nash that there should be a way to make a globally smooth isometric embedding. The embedding theorems say that we should not need more than 2n+1 dimensions. So that's 6 boundaries, 6 dimensions, plus 1. But the 1 is for a twist on each boundary. There's 4 ways of going outside each boundary, and each one of them has a twist. So that says there's at least 30 dimensions that are possible, that would be needed. That's a pretty big topological problem. So are we done? Well, there's software available from our GitHub for NC-dist for the G6 distance calculation, and for CS6-dist for the S6 distance calculation. Have we got all the boundaries? It's a little hard to be sure because, of course, sometimes don't know all the answers. One of the things that Graham pointed out earlier is that this is harder when there aren't 90 degrees. The triclinic problems are harder. The ones where there's 90 degrees does simplify this a lot. So the other thing that we want to talk about here, and this is where Herbert's going to come in, is a piece of software we call NearTree. And we use it frequently in our work. We use it a lot. And the software SAUCE for searching for unit cells that is online stores all its data in trees. So with that, are we ready to go, Herbert?
Sure. You can't have all the fun. Okay, so if you switch to the next slide, please, Larry. Thank you. Okay. Larry not only gets to have the fun of doing the talking, he gets to make sure we end up on the right slide, because I'd screw it up. A near tree is a very, very simple tree. It's also called a bisector tree. In computer science, the basic idea in trying to convert anything that's linear into something that's logarithmic is find a way to stick a tree in there. In this particular case, whatever our metric space is, we know what's near what. So take 2 arbitrary points. Find the plane that bisects them. Things on one side of that plane are nearer to one of the points. Things on the other side of the plane are nearer to the other point. Do that recursively. That's a very simple, very standard way to speed up your searches. Convert exhaustive linear searches to tree-based logarithmic searches. NearTree from Kalantari and McDonald is very, very effective for these problems. As a matter of fact, it's effective for a lot of problems. It works very, very well. It adds a little bit to the data structure. One of the most important things that it adds to the data structure of keeping track of the tree is it keeps track of the maximum distance from the node you're on to the bottom of that segment of the tree. And that allows you to do a major prune of a lot of searches. The other thing you can make use of is there's a metric space we're working in. Use the triangle inequality and use that a lot. And that allows for fairly efficient searches, provided you can compute a distance reasonably cheaply. When we first did this, we took the niggly distance and we computed that, and we made a metric called NC dist. And it wasn't impossibly slow. And we used a bit of a Nash embedding. There's a lot of combinatorics in it, but it was slow. Since the recent changes we've been doing, where we're using S6, the metric that we're using, the calculation, is a great deal faster. So it has been very, very helpful in doing exactly what Larry described at synchrotrons. All right. My main concern most of the time these days is trying to make macromolecular crystallography run faster. Speed is really, really important. Near tree is a very fast data structure, doing your search. If the metric itself is fast enough, having lots and lots of cores helps if the metric itself is fast enough. The S6 distance, the calculation time, is 1 to 2 orders of magnitude faster than the calculation time for the niggly distance. So we tend to use that. It is helpful, okay? The search operation in a tree, a lot of you are computer science, I'm sure you know that. The important point is the performance. If you build it as a tree, it works well. But you can take a tree, and if you present your data in the wrong order and follow the rules of go nearest this node, nearest that, you can run everything down one side of the tree, and it just became linear again. You don't want that. So what we do in near tree is we don't do our insertions immediately. The insertions are deferred until we have enough to just randomize the order of insertions to avoid this phenomenon of everything being on one side. So you try to begin your tree with two things that are far apart, and then you try and stick things under it, which, follow that pattern of keep the tree to a minimal depth. Now, quite frankly, our current algorithms, we don't get a true minimal depth, but we get to, at worst, about twice the minimal depth. It's quite reasonable. There's a problem here, however, and that is that very, very useful search parameter, MACSDist, makes deleting a node very expensive. So what we do right now, the latest version of near tree, doesn't actually delete nodes. It maintains a Boolean which says whether a node should be deleted to maintain the structure. So we have, basically have an exclusion Boolean. And that exclusion Boolean allows us to have the effect of deleting nodes, which allows for the update of a tree. At some point, though, you will have to do a fairly expensive rebuild of the tree when you've gone too far. I think, Larry, I've said enough on near tree. It's your turn to finish up.
So first thing was we want to acknowledge Frances for her copy editing, Elizabeth for doing her drawings of me on the first slide, the spiral timeline and the torus. And thank you again, Vitaly, for inviting us to give this talk.
Okay, thank you very much for your joint and nice talk. Let's clap for Larry and Herbert.
And I should point out that the reference for this, if you're interested in the software, is Vitaly's kindly put our slides on the website for MACSMIN.
Yes, indeed. If you look at the website with all abstracts, then for Larry's and Herbert's talk, there is a link to the slides on some Google Drive, so feel free to download. Indeed. Thank you very much again. And questions for Larry and Herbert, please?
Yeah, can you hear me?
Yes, Michael,
Yes.
please.
Yeah, what I wanted to ask you was, so just making sure I've understood the big idea that you can just take two arbitrary crystals and get a distance between them. Is that correct?
Yes.
Yes.
So, so what I'm interested in is machine learning and property prediction with crystals. And what I was curious about was if I have a data set of crystals, let's say I've got 1,000 crystals, could I use your distance metric as a kernel function to do principal component analysis and create a lower dimensional metric space where each crystal is a point within it?
I don't see the reason why not.
Yeah, okay.
You want to say, Herbert?
Could you clarify if this distance is between lattices of crystals or between really crystals, including points in the motif?
Distances between lattices, I think.
No, I am asking Larry and Herbert.
Oh, right, sorry.
Herbert?
Okay. The distance we use for crystallographic structure solution problems is normally the distance between the primitive reduced cell of one thing and the primitive reduced cell of the other, as normally done in single crystal diffraction. There's no inherent reason why you couldn't do it with anything more general, in which you could be defining something which basically corresponds to a unit cell. We are in fact using very literally the very old-fashioned crystallographic unit cell.
Right. And could you clarify this concept of niggly distance, which was mentioned several times? So what is it exactly? Do you have a formula?
We have an algorithm.
Okay.
All right. You have 15 boundaries to deal with, one of which I intensively hate. It's called the F boundary. And this then generates something which is, it could theoretically be handled entirely as a Nash embedding, but we don't. There is some use in the algorithm of an embedding and a lot of combinatorics, because actually it's faster.
I see. And this niggly distance, have I understood correctly, it's the shortest distance or geodesic distance on a space, was it G6 or S6?
This is the niggly distance is in G6.
G6.
In what we call the niggly cone.
Right.
The niggly cone is unfortunately, two pieces which interact badly.
Right.
Okay. The code works sufficiently well for macromolecular crystallographic cells. For example, Stenkamp and a colleague discovered that there were 3 structures in the protein data bank for phospholipase A, I think it was, okay, which supposedly were in different space groups, and they aren't. They're actually the same. They're actually the same structure. And if you use the older searches that basically just use ABC, alpha, beta, gamma, and some, minor perturbations, you can't see that. It's invisible to you.
Yes.
Okay. And one of the nice things about CS6 dist as opposed to NC dist is that it produces pretty much the same results. There's some distortions in the space. Some things get inverted relative to each other, but it successfully identifies those 3 in the protein data bank as belonging together.
Well, the interesting thing to me was that when we did that search, we found 2 more.
Yes. It works. For macromolecular crystallography these days, it is critically important to find early on structures that are close to the one that you've got in order to do what's called molecular replacement. And you know, it doesn't have to be a perfect similarity. We've done molecular replacement successfully with things that are only 20% similar. But it has to be something which you know, basically allows you to be solving a structure which has enough in common that if you distort enough, you can actually start getting phases out. And it's well worth doing. And just doing it on the unit cell with a good comparison technique, you know, like CS6-DIST, allows you to do that quickly. And when I say quickly, I really mean quickly, because we are trying for, at one synchrotron beamline, to get up to 1,000 structures a day. So it really matters.
I wanted to point out that the two structures that Graham talked about, where they had a cell that was very flat, I think it had a 32-degree angle. I'm sure if you put these into our software, you'll find the distance between them is minuscule.
Okay. Right. So thank you for your answers. So let me stop recording.